you like make sure it's airtight or whatever, so that way the volumes will stay the same.
Okay.
And then before you seal it, you put the fire in the beaker. Make sure the egg's on the top of the flask, and then once you seal it, the pressure should change.
Okay, so I'm going to have fire down here in the beaker, and the egg is supposed to be here or here, like I have it? Okay, so if I have fire down here, you're thinking that the egg's going to travel down and out.
Yeah.
Okay, so I heard some other ideas similar to this. I'd like to hear the other ideas before we actually talk about what that means. Carlos, do you want to share since yours is kind of similar?
The other way around, like have the flask up. That's what I'm saying. So that you like make it
Launch.
So you're thinking, if I heat it enough down here, you're thinking it could come out? That's what you're saying? Okay, Carlos, was your idea similar to Logan's? Okay, but you had something different. What was your plan? Shh. Please be respectful.
You can get the same type of flask and then put it under, and then you could do the same thing that you did yesterday. And while it's coming out into the middle, you can have it right in the middle, and you take off the top, and then you can pull off the air there while it's in the middle of the top.
Okay, so you were saying we're going to put a flask down here, put some paper in it, light it, and then right as the egg sort of travels between the two, separate them and grab the egg. Okay, so what was your idea over here, y'all? I talked to you about this. What did you think? You said something about heating it where? Jasmine, where did you say we were going to heat it? Or Perla? Up here. You were going to heat it, right? Or here, there was an idea of here too. And then we were thinking that that would cause what? Okay, to slide out. What did this table say?
What I said was you have it in the same position as you have it right there, and you lit the napkin on fire and just hold it under, and I guess the heat would extract the egg out.
Okay, so again, we're talking about heat down here. So we have 3 tables that are ultimately talking about putting heat this way, and 1 table that's talking about heating from the top.
Does the egg seem more attractive to put it on top of it? Like it looks like
Okay, so we are thinking from yesterday that the egg was following heat, is what Steve been saying. What was your idea for this table, how you would do it?
just like the font like it is right now, and then put a heat source under it, and for like a couple or like 10-15 seconds, and then immediately take it away, and like the molecules in the flask will be moving faster than the ones outside, so it'll push it out.
Okay, so you were trying to take a differential down here. So we go from hot to cold. Now that it's colder here, you're thinking the pressure inside the flask and then push it out. Okay? What did this table say here?
Oh, you just said break the flask.
Okay, so the task was to how to get the egg back out of the flask. Okay? So what I want you to think about is when I increase heat, what does that do to my gas molecules? Speed them up. Okay? So if I have gas molecules sped up right here, what is that going to do to this egg?
Push it up.
It's going to push on it, right? The gas molecules are going to collide with this egg and push. Do we want to push this egg back up into the flask? No. Okay? So I want to talk about the idea more from back here at this table. So if I heat it here, what does that do to the air molecules inside the flask?
Increase the pressure.
Makes them go fast and they collide more with the sides of the flask and the egg. Okay? So if I have higher temperature in here than out here, right? What does that mean about the pressure inside this versus the pressure outside here? It's higher inside the flask. How do I know that? Okay, so when temperature rises, pressure rises. Okay, so if I have a higher pressure inside here, those gas molecules collide with the egg. Do you think the egg might then slide out? Okay, so I want to show you a really quick video. So, I'm glad that you all were talking about heat and pressure and trying to think about what was happening. I want us to just double check that we're getting this idea correct. That is, heat happens, molecules move faster, which means more collisions. And I want you to think about what that means for pressure. We're going to see another example of it today. So right here we have a sink. We have a bottle with an egg inside, okay? The gentleman who's holding this is going to pour hot water. The reason I know that is you can see steam. You may not be able to see it, okay? But he's pouring hot water over this, so hopefully you can see that. The sound isn't important, so. You see the steam off the sides? And the egg comes out. Okay? So, hot water being poured over the bottle, and the egg pops out. Okay, so we're going to keep these ideas in mind: temperature, pressure, volume. But now we're going to look at another example. Okay, so in the back, I have a can with a little bit of water on a hot plate. Okay, I'm going to put that into ice cold water. Okay, but I have some things I want you to think about while this demo is happening. I want you to think about our variables. What is staying constant? What is changing? Okay? Temperature, pressure, volume. Okay? So at our tables, we're going to keep that in mind, and we're going to come back here and see if this is ready. Okay. So if you need to move so you can see more, that's fine. It happens pretty instantaneously, okay? So, Cynthia, what can you see coming out of the can? Steam, okay? So there's steam coming out. What does that mean about inside the can? Boiling, so it has to be really hot, right? Can you envision what the gas molecules are doing inside this can right now? Okay, so think about the gas molecules and how they're moving. I'm going to take this can and I'm going to turn it upside down and I'm going to stick it in ice cold water. Okay?
Hold up.
Okay, so can you see, everyone see that the can is now crushed, all right? So I want you to think about the variables that we're changing from here to here, and how is that affecting that this can is now a different shape or size, okay? So I'm going to post some questions up there to help you think about it, and I'm also going to post that you draw a picture to help you visualize the gas molecules, okay?
Is your actual box up right now?
So do we have some ideas about what we think might have made the can crush?
The gas molecules inside, like when it was heating up, they were like moving really fast. And but once it like reached to the cold water, it kind of reacted fast and they all came close together. So
What came close together? Okay, gas molecules came close together. And so how is that going to make the can crush?
because with the pressure, like once everything the middle,
Okay, so you're thinking about the pressure outside versus the pressure inside the can. Sort of like think back about the egg, the pressure outside versus inside, okay? So see if you can use the words pressure, temperature, volume, and gas molecules to write what you think happened. Draw a picture, something so you have it down. What ideas have we come up with over here? I see you two gentlemen in a deep conversation. Okay, so you're saying the pressure's staying constant, but you're saying the volume's changed. Okay. Does anyone agree, disagree, think that that's true?
You said what's the pressure stayed constant. The volume changed. I don't know if it did because that's why the volume changed. The pressure changed.
Okay, so now,
Wait, could it be like temperature also?
I don't know, did the temperature change?
It went in ice water. Pressure, volume, and temperature change for what's in the
So Aaron's saying he thinks all three things change. Alex, what do you think?
I mean, the volume change obviously because of the can did whatever it did, and ice and heat. I can't explain it, but
So you're saying heat
I
versus
can't.
ice, that's temperature, right? Yeah, that's fine. So now I think that the thing is you all need to decide, did pressure actually change? And why do we think it might have changed?
Oh, I know.
Aaron, do you have a reasoning why you think the pressure changed?
Everything's going on. Molecule inside moving back. I'll try this pressure. It was the when I think of ice cream.
Okay, what do you mean?
But it was something like when volume, when pressure goes up,
Okay.
then the volume went down.
Okay, so that's an idea. So you're thinking maybe the can was crushed by a change in pressure. Okay. We know for sure that temperature and volume change because those are things we can observe. So now I want you to try to picture the gas molecules and envision them on the hot plate versus in the ice water and how that might affect the size of the can. Okay, so let's talk about that. So what have we been talking about up here, y'all? Get me up to speed.
We're saying that not the pressure and volume and temperature change.
Okay, so you're saying all three things change. Do we all agree with that? How do we know? You can help each other out, right?
What David said was the temperature changed, and when the temperature changes, the pressure changes because the molecules are now hitting the barriers
Okay.
and the volume changes.
Okay, so you're saying your reasoning you're kind of using for the temperature and pressure is a law we learned yesterday, right? Okay, so we're saying.
Put them in the ice water there, like instantaneously stop the cold. So that can cause a change in pressure.
Okay. Okay, so you're saying the pressure is decreasing inside the can or outside the can?
Outside. Or inside the
Okay, so the pressure inside the can is less than outside. So what's actually making the can shrink?
The gas molecules banging against the barrier, which is the tin can.
Gas molecules inside or outside? I think this is so weird to me. Don't you think it's weird that air can cause things to be fresh? I don't know. It freaks me out. Oh, that's true. But this seems a little less torturous than a hurricane, right?
I don't get it. They say that the inside shrunk because it got cold, but it was submerged in cold water, so the outside wasn't cold.
So if you were to go back there and touch the air, which you can do, go and feel the air sort of around the cold water, see if it feels as cold as the water. Do you think they would feel the same if you put your fingers in the cold water and then you feel the air around it? No. So, but there is that hole in the can, right? So can you imagine as I push it down in the water, what's going to happen with that cold water? It's going to go inside the can?
There's a hole in it?
There's a hole, it's open. Okay, so then we might have some cold water traveling inside. Do you think that can affect the air molecules in it? But feel free to go back and feel and see.
Exactly, okay.
When the miracle comes back. Sure. Okay, we're going to take one more minute, then we're going to check in whole class.
Or,
Okay, so the gas molecules are in different volumes. What do you mean by that?
or like, oh wait, different. I meant to say different temperatures.
Okay, so the gas molecules, you mean inside the can and outside the can?
Yeah.
Okay, are in different temperatures. Okay, which adds pressure where?
So like from when you get the can and then you put it into the ice.
Different speed.
It's like it all. There's pressure there. Like what's out.
Okay, outside the can is causing pressure. So this, and then you brought up speeds. How does that come into play with this?
Down up here it's moving and it's constant, and down here it's just
What does down here mean?
like just the